Okay, 5.3 is the last section that's going to be on our third test. It's an alternate form for solving linear systems using matrices. So first we need to talk about what a matrix is. A matrix is a collection of numbers organized in such a way that you have rows and columns inside what looks like a large set of brackets. Every matrix will have a certain number of rows and a certain number of columns. And the I and J next to these, AII, just means, for example, this is A11 because it's in the first row and first column. The point is that everything in the same column will have the same number, and everything in the same row will have the same number there. But that's why the numbers match up for some of those terms, but not for others. Okay, so there's something that we first need to talk about. The thing we use most in this section using matrices is called a determinant. Every n by n matrix, meaning it has to be square, so the same number of rows and columns, is associated with a real number called the determinant, which is denoted, it looks kind of like absolute value bars around A, where A is the matrix. To calculate the determinant of a 2 by 2 matrix, you simply multiply the downward diagonal from left to right, and then subtract the downward diagonal from right to left, which is what this stands for. So if we have 3, 4, 5, 6 as a matrix, the determinant of A is, we'd multiply 3 times 6 minus 4 times 5. So that's 18 minus 20, which is negative 2. Pretty simple. For example, we'll skip 2, but we can do 3. 1/2 times negative 4 minus 12 times negative 1/3. Yes, we can deal with fractions. This is negative 2. Minus a negative is going to be plus, so plus 4, which is 2. So the determinant of this matrix is 2. So the 2 by 2 determinants are not very bad to calculate. They get more and more complicated as they go. Much like systems of equations, solving 2 by 2s is pretty easy. The 3 by 3s are a little bit harder. The same goes for the determinant of a matrix. 2 by 2 is pretty fast. A 3 by 3 is a little scarier looking. So if you have a 3 by 3 matrix, to find the determinant, you have to take essentially each number in a row or column and multiply it by the unrelated 2 by 2 matrix. This is determinant. That means is I need to go either across a row or down a column. If I'm using the first row, I start with A11. I essentially have to cover up everything in the row or column with A11, which leaves me this 2 by 2 matrix. So everything that's not in the row or column with A, and I multiply the determinant of that thing times A, and then I keep going for the rest of the row or the column, giving me this scary looking formula, A11 times A22 times A23 minus A32 times A23, and so on and so forth. Now we're going to actually learn the easier way to do that, so this formula looks scary, don't freak out, but it's important you know what the unrelated 2 by 2 matrix is. It's just the ones that don't share the row or the column with whatever term you're talking about. So find the unrelated matrix to A11. Again, you cover up A11's row and column, and you're left with 4 terms. So the unrelated 2 by 2 is A22, A23, and then A32, A33. From a numbers perspective, what you notice is that none of these share the first number with A or the second one because they can't be in the same row or column. What's the unrelated matrix for A23? Again, if you covered up the second or the third column and the second row, you would get A11, A12, A31, and A32. And lastly, A31, you cover up the first column and the last row. That leaves the top right corner. So A12, A13, A22, and A23. Usually you need to know this for finding the matrix, but again, we'll talk about an easier way to do the matrices when we're trying to find the determinant anyway. Okay, so find the determinant of the following 3x3 matrices. So instead of doing that complicated formula, my suggestion is to always do this. It has the exact same effect. Take your first two columns and rewrite them on the right side. So 681 and 292. Every single term you're talking about, all the positive terms, were the term in the left diagonal for all of the unrelated matrices, which means this term was positive, this term was positive, and this term was positive. So all the top left to bottom right diagonals were positive. So multiply all of those together. We've got 6 times 9 times 0 is 0. 2 times 3 times 1 is 6. 4 times 8 times 2 is 64. That's 70. All of the ones that were top right to bottom left on here were the negative ones. So that's all the blue lines here. And so these were all positive. These ones are all negative. 4 times 9 times 1 is 36. 6 times 3 times 2, also 36. 2 times 8 times 0 is 0. So this totals to 72. So all of our positive ones add to 70, all of our negative ones add to 72, so you just take the difference. 70 minus 72 is negative 2. So the determinant of this thing is negative 2. Much easier than plugging all those numbers into the formula, trying to figure out your unrelated matrices. This works only for 3x3s. Don't try this with 2x2s. It's just how it works here. That's the shortcut we'll use. So again, you rewrite your first two columns. All the top left to bottom right diagonals. So these are the positive ones that you add together. Negative 2, negative 4, that's 8 times 2, which is 16. Negative 3 times negative 3 is 9. Times negative 1 is negative 9. Negative 2 times negative 1 times 0 is 0, so this is 7. The negative ones, when we add them all together, negative 2 times negative 4 is 8, times negative 1 is negative 8. This one was multiplied by 0, so there's a 0. This one is negative 3, negative 1, so that's 3 times 2, which is 6. These add to negative 2. Now, what happens when you subtract these? You take the positive minus the negative, 7 minus negative 2, which is 9. So that means the determinant of this matrix is 9. Not too bad. Okay, let's talk quickly about the cofactor. Find the cofactors for the given elements in A. Cofactor is just, in that other equation, it's basically a positive-negative grid. You start positive in the top left, and every time you move over or down, it changes signs, changes back, and so on and so forth. And these are your cofactors. It's for the middle term. You don't have to worry about it so much, but when I ask you, this is what it is. So for the 6, it's a positive or a positive 1. For 3, it's a negative or negative 1. For 8, it's also negative, a negative 1 multiplier. This can be done with algebra as well. Solving matrices, for example. You don't have to do this way. There's no way for them to know which way you use it, so just use your normal determinant form if they tell you to use second row or third column or anything like that. Find the determinant given the following 2x2 matrices and solve for the variable given the value of the determinant. So we know the determinant is going to be 7 times 1 minus x times 2, or 7 minus 2x. We said it's equal to 12, so we set it equal to 12. Subtract the 7 over, negative 2x is 5, which means x is negative 5 halves. So that means if x was negative 5 halves, it would make that determinant work. Now technically we could also do it with more algebra. Here we have 3x times x minus 5 times x. That's 3x squared minus 5x, supposed to equal 2. Move the 2 over. 3x squared minus 5x minus 2 equals 0. Now we've got a quadratic. This is going to be 3x and then plus 1 and x minus 2. That means I've got two solutions here that work. Either x is negative 1/3 or x is 2. So two different numbers could give you that same determinant. And we will continue this in regards to systems in the next video.